Seminar, and today we have an excellent talk that Kevin gave at FPL, and I'll let Kevin take it.
All right, thanks very much. So, morning everyone. So today we're talking about the paper that we presented at FPL, which is Tighten Large and Complex Benchmarks in Academic CAD. So, to start off with a brief outline. I'll discuss some of the motivation behind this work. I'll then discuss the hybrid CAD flow that we developed and the benchmark suite we created. I'll then go on and discuss how we were able to compare VPR and Quartus 2, and finally finish off with some conclusions and future work. So one of the things that we do in FPGA Research is we want to be able to compare quantitatively different FPGA architectures and different FPGA CAD algorithms. And the way we do that is typically with a CAD flow like this, where we have some hypothetical FPGA architecture, we have some set of benchmarks, and we map the benchmarks onto the architecture using some CAD flow. We analyze the results, and then go back and improve our architecture or our CAD flow. So traditionally, a lot of the focus has really been on the FPGA architectures and on the CAD flow. And as a result, the benchmarks have been kind of neglected. But it's important that we have good quality benchmarks when we're doing these kinds of experiments, because we want to make sure that we're optimizing for realistic problems. So some of the things that we might want in a good benchmark set would be benchmarks that exploit device characteristics. So on modern FPGAs, things like hard blocks. And we also want to make sure that they're comparable in size to modern devices, so that we're solving problems on the same scale as exists in the real world. So the next question is basically, what is the state of FPGA benchmarking at this point? So one of the most popular FPGA benchmark sets are the MC&C20 benchmarks. They were released over 20 years ago. On modern 28 nanometer FPGA, they fill up less than 1% of the device. Some of the circuits are purely combinational, and they make no use of hardened blocks. A more modern benchmark set is the benchmarks that come with the VPR flow. These are somewhat larger, but still fill on average less than 5% of a Stratix device. And they make use of some hard blocks, but really not that many. So these really aren't quite what we want in terms of good quality FPGA benchmark sets. They don't use that many hard blocks. And the size is only going to get worse when we start thinking about future device generations. So the question at this point is basically, why are we at this point? Why don't we have better benchmarks? And the reason is basically that the academic tools have been very poor at handling real-world designs. The academic tools typically have very limited hardware description language support, and they have no library of IP cores that many designs use. Now the vendor tools do support all of this. But they're really too restrictive for our research purposes. We're stuck targeting the FPGA vendors' specific architectures, and we can't go in and modify the CAD algorithms because all the tools are closed source. So what are our options if we want to work around this? Well, one option is we could try and upgrade the academic CAD tools. This would mean adding support for Verilog, System Verilog, VHDL, creating a library of IP. But it should be fairly obvious that this isn't really practical. This is a huge investment. And the vendor tools have large teams of fully employed people that work on supporting this. So what we thought at this point was basically, it would be really nice if we could somehow exploit the strength of the vendor tools, but still have the flexibility of the academic tools. And so this is where we came up with the idea of developing a hybrid CAD flow, where we use a commercial vendor tool to kind of handle the interface to HDL, and then pull the design out of the vendor tool and put it into an academic CAD environment. So how do we actually go about building this type of hybrid CAD flow? So I've outlined some of the major steps in the conventional FPGA CAD flow, and I'll go through them each step by step. So analysis and elaboration is the part where you're parsing Verilog, figuring out what it means. This is the part that we really don't want to have to handle in academic environments. So this is something that we decided to do with Quartus 2. Now ideally, once we had finished analysis and elaboration, we would be able to pull our design out of the vendor tools and bring it into the academic tools. But it turns out this isn't really possible with Quartus, and we also have to do technology mapping in Quartus. But once we've done technology mapping, we can pull our design out of Quartus and bring it into the academic tools. And so what we get is a post-technology map netlist, which consists of basic device primitives like lookup tables, flip-flops, and multipliers. Now once we have that netlist, we can then go on and finish the CAD flow doing packing, placement, and routing in an academic tool like VPR. So the next question is basically what are the capabilities and limitations of this kind of CAD flow? And so we're going to basically compare our hybrid CAD flow, which we call Titan, with the VTR flow, which is a purely open source flow. Now we share a lot of the common tools with the VTR flow, so we can do a lot of the same architecture experiments that we could in VTR. So if you want to vary things like your device floor plan, say you always want your RAM blocks to be next to your DSP blocks, that's perfectly possible. If you want to change your inter-cluster routing network, you can also change that. If you want to change your clustered logic block size, say you want 20 flip-flops and lookup tables in a logic cluster instead of 10, you can do that as well. You can also vary the intra-cluster routing network, so how those flip-flops and lookup tables are interconnected. If you're willing to run your netlist and resynthesize it through ABC, you can potentially change the lookup table size and even introduce a new type of logic element. For RAM blocks and DSPs, we can vary the size of the RAM blocks with some limitations, and you can also change some of the aspects of the DSP blocks, like how many multipliers there are per block. Now the biggest limitation of our Titan CAD flow is basically that we can't introduce new primitive types in the netlist. And this is because there's no way to have Quartus 2 actually generate a netlist primitive that is not built into Quartus. So once we developed this CAD flow, we collected a bunch of benchmark designs in HDL, and we ran them through the flow, and basically selected 23 of them to make this Titan 23 benchmark set. So these come from a wide range of application domains. Some of them are listed here. They include things like neural networks, hashing, matrix decomposition, and many other applications. They all make fairly extensive use of things like hard blocks, so DSPs and RAM blocks, and they're quite large, ranging from 90,000 to 1.9 million netlist primitives. And to put that in perspective, that's 44 times larger than the VTR benchmarks, and 215 times larger than the MC-NC benchmarks. So these are much closer to the scale of modern FPGAs. We can also take a look at kind of what are the characteristics of these benchmarks. So what's the skew in terms of what primitives are used? And so we see that we have some good variety. We have some designs that make use of a lot of logic. We have other designs that use a lot of on-chip RAM, and other designs that make use of DSP blocks for computation. So the next thing that we thought about doing was basically finding a way to compare VPR and Quartus 2. Since we already share a large part of the CAD flow with Quartus, it would be interesting to see if we could find some way to compare them. So what's shown here is basically the conventional Quartus flow. And what we're going to do is basically add in our Titan flow and basically use Quartus map to do analysis, elaboration, and technology mapping, and then complete the design implementation in two different tools. So one being Quartus and the other being VPR. Now, for VPR to actually run on our benchmarks, we have to make some kind of compatible architecture. And the only real restriction here is that you must use the same primitives as are produced by Quartus by logic synthesis. But how you connect these, how you build your architecture of these primitives, is really quite flexible and pretty much up to you as the architecture designer. So I've listed some of the primitives here. These are things like lookup tables, D flip-flops, multipliers, accumulators, RAM blocks, and so on. So these are still fairly generic primitives that you can work with. So in our interest, since we want to try and compare VPR and Quartus, what we want to do is basically have them target, at least as close as possible, the same FPGA architecture, so it's a fair comparison. So we decided to make a model of Altera's Stratix 4 FPGA, and that's an example of what the model looks like run in VPR. So the floor plan on the device, the distribution of primitives and of blocks and whatnot, is based on the largest Stratix 4 device. We fully model the major blocks, so things like the logic block, the DSP block, and the M9K and M144K RAM blocks. For the routing network that connects all of those blocks, we model it as a mixture of long and short wires, similar to Stratix 4. Looking a little bit more at the details of the modeling, for the logic array block, we try and model as much of the internal connectivity as is practical. Although we did have to make some approximations, particularly using full instead of partial crossbars, and also had to, because VPR didn't support carry chains at this point, add some extra connectivity so carry chains would work properly. For the two types of RAM blocks, we support all of the operating modes and sizes, although we did make some approximations to mixed switch modes. For the DSP blocks, we support all of the Stratix 4 multiplier and accumulator modes, although again, we had to add some extra routing flexibility so that the design would pack successfully in VPR. So now we can go on and basically take a look at how both tools did in terms of actually completing some of our benchmarks. So looking at Quartus first, Quartus completed nearly all of the benchmarks, 21 of 23, while VPR completed only slightly over half of the benchmarks, 14 of 23. Now as we look at the two failures in the case of Quartus, those were caused by simply having no Stratix 4 device large enough for the benchmark. So two of our benchmarks are larger than any Stratix 4 device. For VPR, the 9 failures, 3 of those were because VPR was unable to find a routing solution, and the 6 remaining ones basically outran our 48-hour wall clock time limit. So basically ran too long. So it's also interesting to take a look at the performance of the tools compared to the size of the benchmarks. And so we have VPR as the blue dots and Quartus in the red dots. So as we can see, VPR is slower, takes longer time to run than Quartus 2. And particularly, you'll see that there are no blue dots in the large benchmarks because those were the ones that VPR didn't complete. And I put this in perspective. The largest benchmark that we were able to complete, in this case it was in Quartus, took 36.5 hours to run. So if you were a designer trying to iterate on this design, say you want closed timing, as soon as you hit compile, you basically got to wait 2 workdays before you get an actual result back. So this is why we want to use large benchmarks so that we can try and address some of these compile time problems. Another aspect of tool performance is basically looking at memory usage. And here, again, we see that VPR uses more memory than Quartus, in some cases substantially more. But we can also see that it's also more inconsistent. So Quartus tends to scale quite nicely with the size of the benchmark. VPR is much more inconsistent in how much memory it will use. And we can break out basically how much memory is used by each step of the CAD flow in VPR. And basically what we conclude is that peak memory is usually in routing, although packing and placement are actually not that far behind. So it may seem that there is some type of global data structure perhaps in VPR that gets quite large as the netlist size grows. So we can also take a look at the normalized average performance of the tools. So looking at how much pack time, we can see that VPR is about 13.3 times slower than Quartus at packing the design. But in contrast, placement is about 50% faster. Although we'll see that this isn't necessarily at the same quality level between the two. Routing was on average 3.4 times slower in VPR. And the net result in terms of overall runtime was 2.7 times slower. Now, peak memory, as we saw, could be quite a gap as well. And in this case, we found it was about 5.1 times on average. And to put that number in perspective, this is the 5.1 times is the difference between running your benchmark on a 16 gigabyte machine or having to run it on a 128 gigabyte machine. So in running these benchmarks, memory was actually one of the big challenges. We can also take a look at how the performance, how each tool spends its time. And perhaps unsurprisingly, given the high slowdown, how much slower VPR is than Quartus 2 at packing, we see that VPR spends the vast majority of its time, nearly 80% of its time doing packing, with the remaining 20% spent on placement and routing. Quartus 2, in contrast, has a more even runtime distribution, spending just slightly over half of its time on placement. And the next largest component, 21% of the overall time, is actually what we categorized as miscellaneous, which is time spent by the tool that isn't packing, placement, or routing. So it's also useful to try and get a gauge for the relative quality that these tools are producing. So looking at the number of logic blocks used, we found that the VPR actually used about 30% fewer logic blocks than Quartus 2. And as we'll see, this is somewhat related to the wire length gap as well. For the DSP blocks, VPR had more trouble packing the DSP blocks efficiently, so it ended up using about 2.3 times more. And somewhat similarly, the NLMK RAM blocks, VPR used about 20% more. Now, perhaps the most surprising result that we found when we were looking at this was basically that the wire length gap was so large, so it's about 2.6 times. So VPR is actually using substantially more wire than Quartus 2 to rep these benchmarks. Now, one of the things that we noticed when we were looking at those results in more detail was basically that the designs where VPR used substantially fewer logic blocks than Quartus 2 were the designs that typically had the largest gap in wire length. And so this kind of made us suspect that something related to the clustering was affecting the wire length. So what we were able to do is basically adjust how densely Quartus 2 packs its designs and see how the relative wire length changes. And the conclusion from that is basically that if you're willing to pack your design 23% less densely, then you can get up to a 1.8x reduction in wire length. So it seems that really focusing on packing a design very tightly to minimize the number of logic blocks you use can be quite detrimental to wire length. And so we tried to come up with an explanation for why this is the case. So in the top diagram, we can see what's a conventional academic basic logic element. Here you have a lookup table driving the flip-flop, and there's really no way to use the flip-flop without also using the lookup table. In a more Stratix 4-like architecture, there's a lot more flexibility to the design, and so you can potentially pack both the lookup table and the flip-flop independently. And so this means that it's possible, if you're really focusing on reducing the number of clusters used, to pack unrelated logic together. And this is what we think is being detrimental to wire length. So in this example, we have some unrelated logic being packed in an almost full cluster, and that's going to hurt our wire length. Whereas in contrast, if we had spent an extra cluster, we could have reduced our overall wire length. So this is what we suspect is the problem with the packing density and wire length. So to finish off with the conclusion, we've presented the Titan flow, which is our hybrid CAD flow that allows us to use commercial vendor tools to do front-end synthesis, and then bring our design into open source and academic tools. We use this flow to basically create a set of 23 large benchmarks that we think significantly improve the state of open source FPGA benchmarks. And finally, we were able to perform a comparison between VPR and Quartus 2, and targeting a similar Stratix 4-like architecture. And our overall conclusion was that VPR was 2.7 times slower, used 5.1 times more memory, and used 2.6 times more wire. And finally, we basically identified that focusing on achieving a very dense packing is a large factor in that large wire length gap. So from this, we can draw a couple of potential things to improve in VPR. From a performance perspective, improving the runtime of the packer would be useful, because this might allow us to successfully run some of the larger benchmarks, which ran over 48 hours. It would also be useful to bring down the peak memory usage of the tool, because this would make it easier to actually run these benchmarks. From a quality and modeling standpoint, it would be nice to have some sort of way to adjust the packing density in VPR, so that if you want to focus on area minimization versus wire length, that's more user selectable. And also a more flexible description of the routing network would be useful, so we could more accurately model the routing architecture of Stratix 4. Now in terms of future work, so basically one of the big limitations to all the results that I've just shown is basically that both tools were run without timing optimization. And to be really useful as a benchmark set for FPGA architecture and CAD, we really want to make this timing driven. So this is something that we're currently working on right now. And the goal, the methodology we're going to follow here is basically to try to correlate our VPR timing model with a set of small micro benchmarks that shouldn't be affected too much by the different optimizations in the two tools. And then once we've done that, run our larger benchmarks and evaluate the results and see what quality of timing optimization both tools can achieve. So I have some very coarse initial results here. The big changes in this architecture compared to what I presented before was basically that we've added support for carry chains, and we've roughly correlated the wire and logic delays to Stratix 4. So the first three benchmarks here, the 8:1 mux subtractor and 32-bit adder, are all very small. And we can see that the correlation is reasonably good, at least for the subtractor and the adder. The 8:1 mux, when you actually look at the critical path, what's happening is Quartus 2 is using an extra routing wire that VPR isn't. If you ignore that, the correlation is fairly good. As we go to the larger benchmarks, we see that there's more of a divergence between the two tools, with VPR achieving a worse timing optimization, longer critical path than Quartus 2. Although at this point, it's really too early to make any definitive statements. So that basically concludes my talk. I want to point out that all the scripts and tools that you need to run the Titan flow, along with the Titan 23 benchmarks, which are available in both HDL and pre-synthesized netlists, are all available at the web link. So if you're interested, I would encourage you to check them out. So that's it. Thank you very much.
Okay, we have lots of time for questions. Hopefully lots of questions.
Yeah.
So I'm curious about this. So I know that in Python, you can take the LUT output coming out of Quartus 2 and convert it into BLIF form, so you have access to the logic function.
Yes.
Did you get a chance to quantify how much of the soft logic you can actually convert?
So we actually did that because the only thing that we can't convert from just we can't convert to BLIF.name structure, the logic function, is the arithmetic. So if you're using the carry chain, since that is embedded in the lookup table primitive in Stratix 4. I don't have the numbers off the top of my head, but I think on average the arithmetic made up a handful of LUTs, so maybe 2 to 5%, and the rest should be able to convert with no problem. Yeah.
So how big are these circuits compared, so you had the beginning, you had those pictures, and so how would they scale up?
So it's a good question. It depends on which benchmark you're using. So the smaller benchmarks would fill maybe, smaller ones in my in the 23, of the 23 benchmarks, would fill anywhere from 10 to 30% of the large Stratix 4 device. And the two largest benchmarks are Quartus won't fit them, so they're bigger than any Stratix 4 device.
Can I ask what are those very large designs?
What are they?
And are they open source or?
Yeah, so I have all of the HDL for all of the benchmarks, so you can go and take a look at them. The biggest ones are Gaussian blur, Bitcoin miner, and direct RF. So those are the ones that are the largest ones that we have.
Also, I have another question about the benchmarks. A lot of benchmarks used for synthesis, they don't come with simulation scripts. And usually people don't actually verify that they're correct after doing the synthesis. Do you get any confirmation that the simulation runs after synthesis?
No, we haven't done that. I guess the main motivation is basically that we want to target kind of the physical tools and the architecture exploration. So it isn't as important that they're completely functional correct. We want to just capture kind of the key characteristics of those designs. Yep.
So now that you're targeting a time-driven flow, I can foresee one of the problems you can encounter is if your benchmarks have latches in them, they're going to cause problems with DPR where you throw error out, you'll see a time loop. How are you dealing with it? Are you cutting those paths in Titan, or do you actually have to change the benchmarks to remove the latches?
So we haven't actually gotten to that point quite yet. I've just been doing some very simple benchmarks at this point for the timing-driven portion. We'll get there we'll see when we get there, basically. Because I'm not sure how often that will occur in the benchmarks. And that'll kind of sway one way or the other what we end up doing.
I was just wondering about the wire length result.
Sure.
And I'm just trying to get my head around it. It seems like at the end you said, BPR should perhaps have a density button.
Yeah.
But given the dramatic change, it seems like it should have a cost function that thinks about this naturally.
Sure. I mean, that's another alternative. Yeah. I mean, historically, BPR was kind of built to really try and minimize the number of clusters, and when you move to a more flexible architecture like Stratix 4, that basically can start to hurt your wire length because you can actually pack things very tightly, which may not be the best.
I wonder what that would be. There's some simple way to say, these repulsive functions that repulsion is greater than this. Just don't do it.
Well, yeah, I mean, ideally you want some kind of natural clustering to develop. That's a hard problem. Yep.
About that argument, didn't you also mention that Quartus also beat you on the packing density?
No, I didn't say that. I think I don't think I actually looked at for. Actually, I might have that.
You do have logic elements.
You said it was 30% less. But
So if you basically turn up the packing density in Quartus, you can get it down to about 78% of the original. We can't change BPR, but basically Quartus in its dense mode is fairly comparable to BPR. Yep.
Follow up on the whole packing density wire length discussion. You said that none of this is timing driven right now, right?
Yes.
So this might not be true, but the only reason we care about wire length mostly because we want shorter wires to have better timing. So if you had a timing driven everything, wouldn't that naturally want to choose a configuration that minimizes wire length as opposed to packs things together just because it's cool?
That's possible. However, there's also another aspect to wire length, which is how routable your design is.
Okay, yeah, that's the part I forgot about.
So we did see that 3 of the benchmarks, VPR was able to pack in place but not find a routing solution. So that could be part of the reason for that is that we have this more wire length than Quartus is using because of the dense packing.
Another question?
Yeah.
Is that LU network mine?
Yes.
Why does that have so many clocks?
So
I only have 3. What's going on?
So all I'm recording, if I go back to that, if I go back to this one, I'm reporting the number that Quartus reports as the number of clocks, and Quartus seems to, for DDR interfaces,
Oh, right.
start counting up a lot of clocks.
That's true.
So then the LU230 is Wei Zhang, is that
Yes.
you? And then that one's at Alex.
Yes.
Which Alex one is that specifically? The ring or the bar?
I'm actually not sure.
It's probably a ring network.
I suspect it's the thing.
Yeah.
But yeah, so a lot of these benchmarks were collected from the academic community, and some from, a couple of them from Altera as well. So I want to thank everyone who provided benchmarks for this, because that really made this all possible.
Is your, in your release, you're releasing an architecture
Yes.
file, I guess, as well. And what version of VPR are you using, actually?
So this, these results were on an early version of 7. If you look at the paper, it actually says the exact revision number that we used. We're working basically off the trunk at this point because it has features like carry chains and stuff that we want to have in for the timing-driven portion of it.
How's all that going? I'm hearing a few stories, but not much.
Well, we're working at it. So, like I said, I had some initial results which were basically for the logic block and the routing, and that's basically it. And so we're working on getting that to correlate, and then going forward looking at the RAM blocks and the DSP blocks, and how we can model them from a timing perspective. And one of the challenges is probably going to be multiple clocks, particularly since VPR really only allows you to have one clock per primitive. That can be somewhat limiting for things like RAMs that might have multiple clocks. So we're trying to figure out what the best way to go about doing that is.
But on the, keep away from the timing thing, which is a big nut to crack. We were saying, one of your future goals is you wanted more flexible routing description inside the block. And
Well, so not inside the block. By that I meant the global routing network. So for instance, in Stratix 4 you have 4 types of wires. You have length 4 wires that run horizontal and vertical, and you have length 20 that run horizontal and length 12 that run vertical. We can only basically model uniform channels in VPR at this point. So we basically model everything as length 4 and length 16 wires in both directions. And also the connectivity in Stratix 4 is such that you can only get on the long wires from the short wires. And that's the kind of thing that we can't model in VPR at this point. So that's what I meant by improving the routing model. Yep.
More follow-up on this whole discussion with benchmark circuits themselves. Do any other circuits use off-chip memory?
That's a good question. Some of them do. Off the top of my head, I know certainly the 2 LUs do. I believe Spark T1 Chip 2 does as well. And probably OpenCV. So you can look at the HDL code to figure out for sure.
Well, the more important question then is how do you handle all of those weird exotic blocks that result from this in your flow?
So they are generated by Quartus. So you can have all sorts of weird things like double data rate, I/O blocks, and basically Quartus kind of gives you a primitive for that. And we don't do too much effort into modeling that, completely accurately. Basically, we make it work in the flow and basically stuff those all into the I/O pad and leave them there. Because the real focus would be mainly on the core performance if you were evaluating this. But it's all supported, so it will work.
How about encrypted IP? Because the DDR controller, for example, has a NEOS processor, and it'll go through a Quartus map because it'll decrypt it, make the netlist. Does that mean you can work on things that have encrypted IP?
So that is one of the limitations of this flow, is that we can't support encrypted IP. Because we dump the netlist out of Quartus, we get it in this VQM format, and if there's encrypted IP in the design, we get an encrypted VQM that we can't process anymore. So if your design does use encrypted IP, you will have to rip that out and either probably replace it with something that's not. So that is a limitation.
So no comparing designs with NEOS for now, I guess.
Not unless Altera unencrypts it.
Yes, there's a few NEOS clones around. So
Yeah, so I mean, you can, if you're willing to go in and modify the design and replace some encrypted IP with some open source equivalent, then that'll work.
Sounds like you need summer students.
So I mean, the nice thing about this though is that any unencrypted IP in Quartus works. So if you are using their floating point units, stuff like that that's not encrypted, you can get all of that out into your netlist without having to go and manually recode it, for instance.
That's cool.
Can you, note play with the hard blocks and convert Quartus to say, just give me this in stock if you wanted a different version of it?
So yeah, so for instance, if you use multipliers, and Quartus will typically just infer those as into the hardened DSP blocks. If you tell Quartus to infer them into soft logic, they'll come out as soft logic in the netlist.
Is there any value to you producing a second version of Benchmarks that did that?
It's certainly possible, and I'd probably suggest that if anyone wanted to do that, the tools are all open source and freely available, so they could go ahead and do that.
I think one of the super valuable things that you're producing here is the post-synthesized net, so nobody has to touch the whole flow.
Yes.
So just on that front.
Well, so I guess the challenge to that is that the benchmarks actually are, the raw net lists are quite large, particularly for the large benchmarks. If you extract the file from the web link, the extracted file is about 33 gigabytes of net lists from a couple hundred megabytes of HDL. So we don't want to quite distribute too much more than just the basic ones. Now we give you the VQM as well, which is the output of Quartus. So if you want to play with how the conversion tool handles it, you can use our conversion tool and play with the options, and without having to rerun Quartus, still generate variations. Yeah.
Eric LaForce wants to know, what does Altera think about this? About kind of using their tool at the front end and kind of hacking some data out of it?
It's a good question. It works, so unless they turn it off, this should be fine, I'm assuming.
So
yeah.
On that note, is it possible to use, say, the Xilinx front end to do the synthesis step?
So, I mean, assuming that you can get the design out of the Xilinx tools and convert it into the BLIF format, which VPR reads, then sure.
And then would it be possible then to very accurately compare which architecture is actually better on average?
And so,
I'm sure they would love it if you published these results too, right?
So I know when I was at FPL, that was certainly, I got a couple of questions like that.
Yeah, I imagine so.
And all I'll probably say is basically that the tools are available, so if you want to go and do that, then go for it.
No, we wouldn't do that. We would run the independent flows. We put the same things in the front end, we run the independent flows, and then spend the next 5 months trying to verify that you ran them in a comparable way that was apples to apples. But you wouldn't, you'd be doing a worse thing to put it into a common, far less accurate modeling of VPR to get that answer. There is a group up at Altera that does that for a living. It's them to tell you.
Well, I know that some of the questions I got at FPL were would it be possible to compare the runtime of Xilinx and Quartus tools, and targeting the same architecture. And my thinking is that it's really maybe not that useful, because if you run it and you find out that Quartus is fastest on the Stratix architectures and Xilinx is fastest on the Xilinx architectures, that doesn't really give you that much information.
Yeah. It's just something that would be interesting.
Sure.
So what's the hard problem you're thinking right now?
Mainly getting the timing model working is the next big step. And so that's going to take some work, particularly looking at how we handle multi-clock RAMs and multi-clock DSP blocks and that kind of stuff.
You published it at FPL?
Yes.
What sort of uptake, what sort of downloads and people using it? What's happening?
I think I've had 40 or 50 unique downloads so far since I put it up online.
And any kind of feedback, or are you trying to?
Yeah, I've had a couple people email me back, just asking general questions, asking, how do I calculate wire length, that kind of thing.
Any other questions? Pizza seems to be arriving, so we will thank Altera for providing